Okay, thank you. First of all, I would like to thank to the organizers for their warm hospitality. This work is a joint work with Professor Anton Baranov from St. Petersburg University. I will use the following notations. D is the unit disk centered at the origin, and also I will use Hardy spaces. And Hardy spaces, Hardy space consists from the functions f, defined analytic functions f, defined on the unit disk D, and this integral is bounded. And let me start with a classical result of Sergei Mergelyan. Obtained in 1951. And as was mentioned by Professor Aptekarev, Sergei Mergelyan was a scientific advisor of Andrei Gончар. And Mergelyan showed that there exists bounded analytic function, in the disk D, such that this integral, double integral g prime of z dz squared is just abbreviation for dx dy. This integral is equal to infinity. Bounded. Yes, sorry. Bounded function, and this integral is equal to infinity. This is non-trivial result because we know that if function is bounded, then we have the following property: g prime of z, Schwarz-Pick inequality is less or equal than 1 minus z squared. Okay? And then if we plug in this inequality into this integral, then we see this integral has at most logarithmic behavior. And it is not so easy to construct such a function, because all simple examples, they show that this integral is bounded, but there are some analytic functions for which this integral is infinity. Then, after that, Walter Rudin in 1955 constructed infinite Blaschke products. With the same property. B is a Blaschke product. Of course, it is infinite Blaschke product. And in fact, this result also can be derived by using this, the example constructed by Mergelyan. Because we can approximate any analytic function by Blaschke products. And also an example, a similar example, but with concrete zeros, was constructed by Roger Iranyan. In 1988. So one may ask the following question: what will happen in the case when we have finite Blaschke products?
When you say the similar result by Piranian, what does it mean? The same result as Rudin, or?
Similar means that he constructed this. Rudin constructed example with just he showed that there exists such Blaschke product, and Piranian constructed with concrete zeros. He just wrote down concrete zeros.
How it looks like, if it's possible to draw?
Oh, I forget, but no, it's very non-trivial examples. But concrete. And both results actually follows in some sense from this result. This result is also shows that there exists infinite Blaschke products with such property. Okay, the question is that what will happen if we consider finite Blaschke products? Or should I? Okay. So suppose that we have finite Blaschke product. B is a product K from 1 to n. And then we want to estimate or evaluate such integral. Such the integral.
Degree.
Yes, of course. And this such integral is of course bounded. It's not so easy. It's not so difficult to show. And of course, this integral tends to infinity, must. I mean, supremum overall finite Blaschke products degree of n tends to infinity, as n tends to the infinity. This follows from this fact. So now there are a lot of papers devoted to such type Blaschke products with p greater than 1, and when p is 1, we don't know such the papers. Okay, so theorem, let me formulate theorem 1. This supremum is comparable to square root of log n. Okay, let me give some remarks. For instance, suppose that B is finite Blaschke product, then it is not difficult to show, and I already mentioned this fact, that So just using this estimate. And of course, at first, let us remark that when we estimate such integrals, we need to estimate only this body, because the rest part is quite easy to estimate when z is greater than 1 minus 1 over n. So if we use this estimate, or just we can write in this form, this integral. So we get immediately this is trivial estimate log n. Then if we modify it a bit this inequality, then it's not so difficult to show that for instance, if we use Cauchy-Schwarz inequality, or just d squared better to use this, better to write it in this form. B prime, and we multiply by square root of 1 minus r squared, and divide by square root of 1 minus r squared. Then just applying Cauchy-Schwarz inequality, we see that this integral is bounded, even it is bounded in the unit disk, not only on this domain. This is bounded, and this gives us exactly this logarithmic behavior, square root of log n. So this shows that we have this estimate. What? Yes, of course. But if you use this one directly, you mean this bounded?
Yeah.
No.
No?
No.
It's more difficult. Oh, yeah, there is a square there.
No, it's just something like some ak squared. It just behaves like some ak squared. And this is, of course, is 1 for Blaschke products. So, but okay, so you see, again, this is quite simple inequality, and one may ask question, maybe there is some more delicate approach that shows that maybe that gives us better estimate than square root of log n. This quite simple estimate, but it turns out that it's sharp. It turns out that it is a sharp estimate in the order sense of order. And to show the sharpness, I don't know, if we work in the space of bounded functions, it seems to me this is a very hard problem, really hard. And maybe it's not easy to solve it. So really hard problem. But if we use the theory of block functions, especially Makarov's theory of the log of the iterative logarithm, then it is possible to show that this estimate is sharp. Okay, let me give you some information about the law of the iterative logarithm. Makarov's law of the iterated logarithm. He proved it in 1985. Suppose that g is a block function. What does it mean? It means that Bloch norm of G, okay, semi-norm, for instance. Bloch semi-norm is just supremum. G prime of Z, 1 minus Z squared, and D belongs. And from Schwarzschild inequality, it follows that bounded functions is a subspace of Bloch of the Bloch space. With this semi-norm, or just if we want, we can obtain a norm. But maybe it's just I will erase it. Makarov shows that in 1985 that upper limit when r tends to 1, g of r this square root of log 1 minus r triple log is less or equal some constant c. In fact, this c is 1, which was showed by Pomerenke, but Makarov showed this inequality. Here is surprising function, this one, because surprising function. And why this is surprising? Because we know that if we integrate this inequality twice, then we have this inequality, something like log. Then if we take a squared, then it will be square root of log 1 minus r. But here we have in the denominator this. Also, I should say that it is, this inequality is valued for almost all that that belongs to the unit circle. So it means that is 1. And there is also important characteristic asymptotic variance. So let me introduce it. Asymptotic variance, it is just sigma g is this upper limit and this function is bounded. Asymptotic variance is bounded because of this inequality, which follows from the definition of the Bloch space. Here we have to multiply by the norm, Bloch semi-norm, or maybe norm. And in many cases, it turns out that one can replace the Bloch semi-norm by asymptotic variance. For instance, this is true for Leconary series, and for many cases, for many functions that comes from dynamical systems. So that, and these are all very non-trivial examples at spaces. And Makarov posed the problem: is it true that if sigma g is greater than 0, then this limit is also greater than 0 on a set of positive measure. On a set of positive measure, strictly positive measure. Because I mean that is it true that for all Bloch functions this property? And this fact we have only for some subclasses of Bloch functions. And Makarov asked, and Felix Pzhetitsky constructed some examples that support this conjecture. And he conjectured that this question has a positive answer. However, in 1991, Rodrigo Bonoelos and Charles Moore, they disproved this conjecture. In 1991, Rodrigo Bonoelos, Charles Moore, they showed that there exists function g such that Bloch function g such that g of z less or equal than square root of log 1 minus r. And okay, sigma squared, okay, sigma f is strictly greater than 0.
So sigma g.
G, okay, G.
What is it? You need the positivity only almost everywhere, or you need to have it everywhere? Because
Almost everywhere.
almost
No, only set a positive measure. But here is, okay, but here, what is this example says? That left-hand side is 0 on everywhere, not almost, even everywhere. Left-hand side is 0. Huh? Okay, absolute value. Or just one have to write in this form, log 1 minus r, okay.
Here there is an extra question. This is probably an inequality, not equality.
This, no. This equality for some classes, like Lacunary series on.
Sorry, the left-hand side depends on theta. The right-hand side is just a number.
Almost everywhere.
almost everywhere. Yeah,
We have almost everywhere.
You mean that the limit is the same for almost
Yes.
And well, in this example, the right-hand side is positive, the left-hand side is...
No, but you know that this for some classes, of course, for all functions, for all block functions, we have this one. This is Makarov log of the iterative logarithm, okay? But for many classes, just like Lacunary series or cases from dynamical systems.
Is for many classes, not for all blocks?
No, of course not. No, of course no. Not for. Just for instance, for Lacunary series, it was proven by Salim Zygmunt and Mary Weiss and Erdős Igal, so that there was a lot of works, and also Felix Przeszycki obtained a lot of results in this direction, as well as Rodrigo Banuelos also. They obtained a lot of results in this direction. But this example, it turns out that this example shows that our estimate is sharp. Maybe. This estimate is sharp. This example shows. Okay, let me demonstrate it. What does mean this greater than 0? It means that g of z squared behaves like, okay, g of r I to the I theta from 0 to pi, the theta behaves like log 1 minus r as r tends to 1. So what we need? We need this relation as well together with this inequality. And then let us see what will happen. We consider this function g prime of z squared, not just this one. One minus or get lower estimate, we can restrict ourselves by this disk. Then we multiply both sides by g square, g prime. 1 minus r squared g prime squared g prime squared or maybe better to use this one. Inequality. This is less than 1, right? We use this estimate. Here is Bloch norm. Okay, maybe here we have to write Bloch norm. This is Bloch semi-norm of B. Okay, and this behaves like this behaves like some AK squared. Or, okay, GK squared. So this we have here k squared, gk squared, then we multiply by 1 minus r squared. So this reduces to 1, and then the next integration gives this inequality.
Sorry, gk are what?
Gk are Taylor coefficients of g. It's rather easy to show that. So gk is g squared. So this, but this inequality, what is this inequality is very efficient for block space, but it is useless for bounded functions. Okay. So, for instance, if we consider such an inequality for bounded functions, suppose that g is bounded. Okay, then this is useless because we want to estimate this integral. Okay, we want to estimate this integral, and for bounded functions, this behaves. This is also bounded. So this inequality is useless for bounded functions, but for block functions, this inequality is very efficient because this gives a solution to our problem. Why it gives? Because this is equal. Approximately equal to or comparable, okay, comparable to log n. Okay, while g of z is less or equal than square root of log n, and then we can divide by this square root of log n, and we obtain a bounded function with such a behavior. So the solution to our problem follows from, or can be demonstrated by using this example.
So could you repeat the main line? So because you mentioned that for bounded functions, this inequality is useless.
Yes.
And then
But for block functions, not.
for block functions, not okay, but we are working with derivative of the Blaschke product, which the Blaschke product is bounded, or you just want to demonstrate how it works if Blaschke product is replaced?
No, just I mean that I mean that relation between bounded functions and Blaschke products. Yes, because any Blaschke product can be, any bounded function can be approximated by Blaschke product. And
I understood, but how it's related to block functions?
block.
Well, this inequality is of interest only for block functions, right?
What?
The inequality on the bottom is interesting only for block functions.
Yes.
And how to extract Blaschke products from how to extract.
No. Okay. So then we do the following operation. We have function g and divide it by square root of log n. And consider the functions, define it. Okay, we consider this function g of rz divided by log n, where r less or equal than 1 minus over n. And then using approximation properties of Blaschke products, then we construct Blaschke products with such the property. Of course, this is maybe this is maybe there exists a direct example without these considerations and concrete example with concrete zeros, but we don't know. But this is rather difficult, and our proof based on this result obtained by Banuels and Moore. Okay, now, so we solved this problem. Now let me inform you about the main topic of the talk. Okay, suppose that omega is a multiply connected domain, bounded by rectifiable curves. Then Долженко, Евгений Прокопьевич Долженко, in 1966 showed that if R is a rational function, is a bounded rational function, bounded in domain D, then this integral r prime of r prime to the p dv squared is less or equal than some constant c by n to the p minus 1. And this is true for p between 1 and 2. And in the case p is equal to 1, we have this estimate, C log n. But
What is n here?
n is the degree of this rational function.
Degree is the sum of the maximal of.
Yes, maximal denominator and denominator. And but he proved this under assumption that this domain has a curvature at each point, and this curvature satisfies some Hölder conditions. So this is quite a restrictable statement. So we proved that with Anton, we proved this result under the restriction only under the restriction that domain has no inner zero angles. So that we proved that this result we prove the following theorem. If omega is a John domain, if omega is a John domain, it rectifiable boundaries with rectifiable boundaries, then these inequalities are valid. Долженko's theorem is true. What does it mean John domain? It means that for any 2 points A from the boundary of omega and B, from omega, there exists a curve gamma such that the length of this curve is less or equal this distance from B to the boundary omega. So this is a definition of John domain. Yes. So A is here, B is here, and there exists curve.
So
Gamma, yes, is a connection between. Yes. Gamma is a connection between A and B, and this domain has. So this is domain without inner zero angles. So this is. We avoid such domains. Sorry. And also we proved in this special case, for instance, theorem 3.
Before you raising, could you comment on what is the difference between assumptions in
Долженко required curvature. So very smooth at each point. And this curvature must satisfy Gilder condition also.
Where is this assumption in Долженко theorem? Okay.
No, just no. Of course, I did not write it. I did not write it, but he required curvature. On theorem 3. Пять минут? Okay. Theorem 3. It is simply connected case. For instance, simply connected case. And phi is a conformal mapping from the unit D onto omega. If phi belongs to H2, then Долженко results are valid. And this integral is less or equal than this square root of log n. And this is sharp estimate.
Sorry, and this constant. Sorry.
What?
This constant C.
Yeah.
Depends on what? It's an absolute constant.
This depends on the domain. Yes, it should depend on the domain. And R is bounded, okay? R is less or equal than 1. And this constant depends on the domain. C of omega. And this sharp result. And we have a question. Is this true for all domains with rectifiable boundaries? Or not? So here is important that phi belongs to H2, Hardy space H2.
Eventually, phi prime belongs to H2, the derivative.
Again, sorry. Yes, of course, right. Because phi belongs to H2 for any bounded function. Or even H infinity. Okay, thank you very much for your attention.
Okay, questions, remarks, first of all, from the audience here. Anybody online with questions or remarks? I cannot see them. I have a quick question about the first theorem when you speak about the Blaschke products, okay?
Okay.
If you look at, say, extremal sequence of the Blaschke products that kind of saturate the square root of log
Yes.
n, is it true that every point on the circle is attracting the zeros of this sequence?
Attracting zero, I don't know. This is, I have to think about.
Okay.
Maybe Anton can answer this question. Anton?
We do not have the answer. I remember there was some small discussion about this Piranian construction. In his construction, the zeros were put on some circle with the radius approaching one very quickly, like exponentially close. But on each circle there was some cluster of zeros and uniformly distributed as vertices of some polygon. And so this was his construction, how to make this integral infinite. But if you look at finite Blaschke products of this type, you can get, of course, some infinite from below, but it's much, much worse with this square root of log n, like some double logarithm, something very, very weak. So we do not know how to approach this cut down of square root of log n by some concrete example. The intriguing question is almost nothing.
Yeah, this is hard problem to get Laura estimate that shows this sharpness of this inequality.
Yeah, okay. Yeah, I also could reformulate it from my point of view. Can you find a measure on the unit circle such that the orthogonal polynomials, when you form the Blaschke product by dividing the polynomial by the reverse, has this extremal behavior? That would be also interesting.
Okay, we will think about it. Thank you for your suggestion.